All right. By this point in the module, you should have two measurements of the brightness of the moon taken days apart. When the phase of the moon, as observed at visible wavelengths to the human eye, was different, significantly different. Now, I'm not going to spend a lot of time explaining the phases of the moon. You learn how this works in elementary school and middle school, and again in high school. But this figure here summarizes it pretty nicely. We have the Earth, the moon is orbiting around it, and the whole thing is illuminated from the sun. So the phase that we see, it's just reflected light, and it all depends on where the moon is in its orbit with respect to the direction of illumination from the sun. For example, if it's here, the dark side of the moon is facing us. We call that a new moon. And as it works its way around the orbit, we see more and more of it until you're in this position where it is fully illuminated. Unless on rare occasion, it is exactly behind the Earth with respect to the sun and in our shadow, in which case that's an eclipse. But normally you don't have a precision alignment. And so you see full illumination, and then it works its way back to less and less and back to new. Okay, so you've made two measurements of the brightness of the moon at two different dates when the moon had very different phases, different amounts of reflected sunlight. For example, suppose the phase dropped from 100% during your first observation to 50% during your second observation. If so, did the radio brightness of the moon also drop by a factor of 2? If it did, you're probably looking at reflected sunlight, at radio waves, reflected radio waves. If it didn't, what you're detecting is something different. In that case, you're not detecting reflected radio waves from the sun, but radio waves emitted from the moon itself. Suppose your brightness stayed fairly constant. It won't be perfectly constant because the moon's distance away from us does change a bit from day to day. But if it's approximately constant, instead of reflected radio waves, we're detecting radio waves from the moon due to its own temperature, its own thermal emission. So this is called thermal emission, black body emission, and you're detecting it from a little bit down into the lunar soil. Radio waves are penetrating. You've listened to a radio inside a building before. That means the radio waves penetrated through the walls to get to the device. The same is true with the moon. If we're picking up thermal emission from the moon, it's not exactly from the surface, but a little bit down into the soil. And many of you have been to caverns here on Earth, and you've gone down into the cavern, and the temperature is always the same down there, day and night, throughout the seasons. If you go just a little bit down, the temperature stays pretty uniform, and the same is true for the moon. So if your measurement of the brightness is not varying, other than the distance effect, then you're measuring the temperature of the moon on two occasions. You're using the radio telescope as a big thermometer. So the next thing we need to do is calculate the temperature of the moon. Now, to do that, you need to know a little bit about thermal emission. And so here we have thermal spectra, black body curves, they're sometimes called. On the x-axis, we have the frequency of the light. This is the visible band. This is light that we can see with the human eye Over here, you have ultraviolet. Here you have infrared. And way over here off the left side of the chart, we have radio. And here you see different curves for different temperatures. Now, your temperature is about 300 Kelvin. That's kind of room temperature. So that's this curve here. You see it does not cross the visible band. And consequently, you're not emitting visible light. You're not glowing. But you are emitting infrared. That's the heat that's coming off of you. That's this curve right here. And for hotter and hotter objects, they do intersect the visible band. And so they glow and they can have colors depending upon whether there's more red light or more blue light. Now, at radio wavelengths, we're way down here, away from the peak in this limiting regime. It's called the Rayleigh-Jeans limit. So if you detect something emitting radio waves and it's a thermal emitter, the brightness that you see depends upon a number of things. It depends on the temperature. The hotter the object, the brighter it will be. It depends on the surface area of the emitting object. If it has more surface area, it's emitting more radio waves. So for a spherical object, the area is proportional to the radius squared of the object. The amount of radio waves you detect also depends upon the distance. The farther away something is, the fainter it will be. So it depends on 1 over the distance squared. And lastly, it depends on the frequency that you're looking at. Clearly, you go to lower frequencies, there's less. You go to higher frequencies, there's more. Anyway, there's a derivation of this here, but you put it all together and solve for temperature, and you get this equation right here. So the temperature of the body depends upon the flux that we see. That's that S. S is flux, sub nu. Nu is frequency. So the flux at a particular frequency. That's what you measured in Janskys. You'll need to convert that to the MKS system. 1 Jansky, you can see it here, is 10 to the minus 26 watts per meter squared per hertz. You take your Janskys, you multiply by that. We have some constants. K is Boltzmann's constant. C is the speed of light. Again, nu, that's the Greek letter nu, is the frequency at which we observed. For example, you might have observed at 1395 megahertz. That's 1.395 times 10 to the 9 hertz. Here's the distance squared. Here's the radius squared. That's pi. And so all these things are known. You've measured this. The others are constants or known quantities. The only thing we haven't figured out yet is the distance. So let's go back to our temperature calculation spreadsheet. And let's fill in some of these things. So again, by this point, you have 2 measurements of the brightness of the moon taken at different dates. I only have 1 here, but that's enough to show you how to do this. Here is the moon's phase, and you can get that from most online lunar calendars. I've linked one of my favorite ones here. And so let's see, this date was January 22nd. January 22nd. To get the illumination fractions, you click here. So 92.6. So it's almost full, 92.6. And your other measurement, it should be very different because we picked a time where the phase would be very different. And you can see if it's changing with the phase, it's reflected light. If it's not, if it's holding pretty steady, it's thermally emitted radio waves. If it's thermally emitted, we can calculate the temperature. To do that, we need to get the distance, and for that, we go to stellarium. So here's stellarium. First thing you're going to want to do is put it in universal time. So click on the first tab, the location window, custom time zone, and set that to UTC. There we go. You can get rid of it. Then let's bring up the date time window. Change this to, for my observation, it was January 22nd. 22 hours, 20 minutes. And then I'm going to call up the moon. And I look for distance, not distance from sun, but distance. And that's the distance from Earth. And we want the kilometer value. That's in the parentheses. Here it says 389,897. Okay. Now we have everything we need to calculate the temperature using this equation here. So doing it in the spreadsheet, it's equal to the measured flux in Janskys times our conversion. I have all the constants you need right here, times the conversion from Janskys into a proper MKS unit, divided by 2, divided by Boltzmann's constant, times parenthesis C divided by the frequency, unparenthesis squared, the whole thing squared, times, let's check our equation here, distance squared, that's this, distance squared, divided by pi, divided by the radius squared. Calculates it for you. So that's 2.22 times 10 to the 2. In other words, 222 is what I got. And so you'll do this for both, and you're getting 2 independent temperature measurements. And if it is thermal emission, those temperature values should agree more than your flux values. The flux value should be a little bit different because the distance to the moon changes from day to day because the orbit is eccentric. Sometimes it's closer, sometimes it's farther. This should correct for it. The temperature should be kind of consistent. It will give you an idea of how accurate your measurements can be, having 2 of them. Now, the last part of the activity is to see if what you got is reasonable. So here's a nice website. You slide down, it has both models and observational data. So I'm going to pick, we're looking at 1.395 gigahertz. That's 1395 megahertz. So kind of between these two. First, let's look at the 1 gigahertz, and we can turn on these example observations. You can see at this frequency, we have a model here and shows it should be pretty constant with phase. It's not reflected radio waves at all. And the model is a little bit crude. I'll just compare to the measurements. You can see the measurements here in the mid to low 200s. So pretty much what I found. We can also check at 2 gigahertz, turn on these observations, again, mid to low 200s. So my measurement seems pretty reasonable. All right. That's it for this video.